Welcome to the Fab Shop. I'm Jason Ball with Miller Electric. Today's video series is going to be on the 7 essential variables in welding. So you're probably asking yourself, Jason, there's a lot more than 7 variables when it comes to welding. And you would be correct in that. There are tons of variables that come into welding. You've got different gas mixtures, flow rates, power input requirements. That's all great and dandy, and you need to know that stuff. But I'm going to a fundamental approach to teach content to new welders. And that's through identifying 7 variables that you control. How this is going to lay out is a 7-part series. So we're going to tackle each component of the 7 essential variables individually, and then we'll keep building on that to get a solid foundation down of what these are, how to control them, and how to use them in your everyday welding school or in your everyday discipline as a welder fabricator out there. So to name off the 7 essential variables, we have wire feed speed, voltage and trim, contact tip to work distance, work angle, travel speed, and placement on joint. These are the 7 that you're going to be able to control from the feeder to the bench. So let's start taking a deeper dive into what these 7 essential variables are and how you can control them. Starting with wire feed speed. Wire feed speed. Wire feed speed. Wire feed speed. On the front panel of this 255 Miller-Matic, I have a wire feed speed adjustment where I can increase the wire feed speed or decrease the wire feed speed. With this type of setting, I can increase the amount of amperage into the part or decrease the amount of amperage into a part. This is going to affect the amount of power input that I actually put into the part by either adjusting this value up or value down. Now, if I'm using a constant current machine, which is like a Synchro Wave 300 here for TIG welding or stick welding, I'm able to directly control amperage by adjusting the value of amperage directly up or down. This still controls the amount of power input I have with the torch, and I control this value by increasing or decreasing that value. So that's the difference that I'm going to see in how I can control amperage between a constant current machine, such as a TIG welder, versus a MIG welding machine, which is a constant voltage machine. But that's how I adjust amperage up or down on the front of these machines. And up next, we have voltage and trim. Voltage slash trim. Voltage. To adjust voltage up or down, I'm going to use the left dial on the Multimatic 255. And this is going to help me determine the height of my arc that I want to have. This is a big driver on my overall heat input. It controls the amount of bead appearance that I have. It controls the spatter levels that I have in this process. But really what I'm doing in CV mode, constant voltage, non-pulse state, is that I'm controlling the height of that arc. When I go to a constant voltage machine that does pulse, I can directly change that length of the arc. We actually call it arc length, and I can increase that length and decrease that length. In this example, we can see that by leaving the amperage values the same, but just by merely increasing or decreasing the voltage, we see a difference in how the bead profile is actually set up. We also see how the penetration profile changes too can be affected by the voltage changes it has. Now that we have the variables understood from the wire feeder side, let's go to the MIG gun slash torch side to look at how we can control the 7 essential variables now on the work end, starting with contact tip to work distance. 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 Contact tip to work distance is the distance from the contact tip surface to the very edge of the surface of my wire. In this case, you can see in the example, this is how far my contact tip to work distance is. I can also vary that by my hand movements in and out. I can increase my contact tip to work distance, and I can decrease my contact tip to work distance. This has a different effect if I'm using pulse. The only thing that becomes an issue is shielding gas coverage, but it really is important in CV welding, where I'm in a constant voltage process. My variation of this stick out is going to cause my power input to change greatly. Experienced welders are going to be able to understand to use that for root passes and things like that, where they can actually decrease their power, increase their power based on this movement. But really, contact tip to work distance is my ability to control this distance here and maintain it consistently throughout the entire weld without too much variation in my up and down movements, very much so when I'm in constant voltage mode. With contact tip to work distance, we can see with all the variables being left consistently and just changing the contact tip to work distance, really greatly increases and decreases the amount of resistance in the circuit, increasing or decreasing the amount of amperage that we can put into it. You can see in the example the change in the weld profile just by us varying that stick out up and down, or the values are also increase and decrease with amperage. Stick out is able to control the amount of resistance in that circuit.
So let's continue down the list to number 4, which is going to be work angle.
Work angle.
Work angle.
Work angle. Work angle.
Work angle is the ability for me to control the angle that is perpendicular to the direction of my travel. So if my direction of travel is this way, I've got a work angle that I've got to decide, or I follow a process that dictates, am I doing this at a 0-degree work angle or a 45-degree work angle or a 10-degree work angle, but it's perpendicular to the direction of travel. Another example of this on a T-joint, this gives me the ability to place the arc exactly where I want to have my penetration profile and how I want to fill in the metal. It's extremely important if I'm doing any multi-stack welding where I have to position the gun in different work angles to be able to stack. But in this case, if I'm coming down this 90-degree, I'm going to keep a 45-degree work angle the entire time with it. That is how we explain work angle. Number 5 on the list is going to be travel angle.
Travel angle. Travel angle. Travel angle.
Travel angle.
Now let's talk about travel angle. Travel angle relates to the direction of travel. Then I'm going to produce an angle of some type, whether it be a 0 angle in some cases. I might need a 10 to 15 degree push, which is very common. Depending on the electrode, it could also be a drag case. But more common I'm gonna find in MIG is gonna be about a 10 to 12 degree angle that I can use so I can see the arc. That combined with my contact tip to work distance being favorable, I'm gonna be able to see the molten puddle. So this is a really critical feature when you tie everything together between my work angle being either 90 degrees, and then I've got about a 10 to 12 degree work angle or travel angle here. And then I've got my contact tip to work distance set. So now by tying all 3 of these parameters together, we're able to produce a weld that is acceptable for our quality standards.
Number 6 on the list of essential 7 variables is travel speed.
Travel speed. Travel speed. Travel speed. Travel speed. How fast can I move this gun? It's not a contest, it's a controlled value. Like, I really need to be able to understand, am I trying to run this at 8 to 10 inches a minute? Or is the weld size and the material thickness I'm working on, does it allow me to move even faster in that 15 to 20 to 30 range even? Robotics, I'm gonna move a lot faster with that, but still travel speed is something that I have to be able to understand and use correctly. How fast do I wanna move? Same thing can be said for travel speed when I'm TIG welding as well. It's gonna be a case of how fast am I able to move with that material type. Obviously with aluminums, it's gonna be hot and fast. And if I'm gonna be on some steel with maybe some silicon bronze or some stainless filler on mild steel, like I'm gonna have a pretty good speed for travel, depending on what I'm using for filler. So, but again, we're gonna combine all that stuff. We got our amperage set for this process. We've got our voltage set. We've got work angle. We've got our travel angle. And then we've got our contact tip to work distance. And then we've got travel speed we're gonna pull into play now.
And that's how we can control the travel speed of this process at number 6. And finally, for our last variable in this series, number 7, coming in last but certainly not least, is placement on joint.
Placement on joint. Placement on joint. Placement on joint. Placement on joint's a good one. Usually people want to mess up on. Placement on joint is the most waffled one of these 7. When I say waffled, I mean this will identify folks that have bad eyesight, which I find is the number 1 culprit, that people have an issue with placement on joint. Placement on joint is going to refer to how my electrode is positioned on the part. In this case, I'm using a tungsten rod as a pointer. But if I have my placement on joint favored too high or too low, I'm going to get an undesirable weld profile that happens because of that. Specifically in this lap joint, if I have my electrode too high on this top piece of metal right here, I pull too much of this material, and gravity takes hold and bloops it on down here. So I should be able to see that I'll get some cold roll or some overlap on this bottom toe of the weld, and I'll undercut really heavily here. Shooting straight in the middle in this case might end up eroding this shoreline, as I like to call it, even more. I may want to do probably either the diameter of an electrode, if not half the diameter of an electrode, away from the wall for my placement on joint, so that I can successfully burn in some of this edge a little bit, but also add some filler material to be able to backfill this space as I erode away a little bit of that shoreline right there. And then I won't get such a raggedy profile right there for it. If my eyesight's really bad, it's going to be hard for me to track this black line in some cases, especially when there's an arc that's present with this. So get your eyes checked, make sure your prescription's up to date, and make sure that you can see the joints you're working on.
So that rounds out the 7 essential variables in welding. 7 essential variables in welding.
7 essential variables in welding.
Contact tip to work distance. Okay guys, cut it out. That's enough. Stop. Now that we've rounded out the list of the 7 essential variables, hopefully you have a better idea of how these variables are used in a simplistic approach to be able to control the welding process in not only your welding education program, but maybe in your everyday life out there as a welder, fitter, fabricator. So I hope you found that this content was helpful and useful to break down the welding process into 7 essential variable steps that you can control as a fabricator out there. I'm Jason Ball with Miller Electric. This has been your Miller Electric quick tip today on the 7 essential variables in welding. Have a great day, and we'll see you next time. Thanks for watching. Almost forgot, leave a comment, a like, a dislike. I'll take negative feedback to help us improve the content and improve the channel. Thanks again for your participation. I'm Jason Ball. We'll see you next time.
And also the 7 that you really need to kind of master in order to really grasp a process in welding. So there you go. There's only 7 of them to practice.
We gotta go fast. We gotta make money. Let's go.
These are the 7. These do good. Notice it's a different color. It's in blue now. I changed it from blue to red. And figure out how we can,
Who's after travel angle?
Closing on number 6 is going to be, I don't know what number 6 is going to be.
Or being a welder, fabricator, or just being awesome. So to wrap this all up, now that we have the cut.